Hi, everyone. Thank you for joining us this morning to learn a little bit more about SigOpt's new experiment management functionality and how it assisted in optimizing a machine learning model for natural language, the BERT model. I'd like to introduce Meghana Ravikumar, who is SigOpt's machine learning engineer who performed this research on optimizing the BERT model for natural language understanding. Okay, take it away, Meghana.
Great, thanks. Hi, everyone. Thanks for joining me today. We're going to be talking about why experiment management is important for NLP and specifically how experiment management helped me in critical aspects of my modeling process for a recent project I did on compressing BERT. So before we jump in to experiment management, let's just go over a quick recap of the BERT compression project. I really tried to answer two main questions. One, can we understand the trade-offs made during model compression? And two, can we find a model architecture that fits our needs? The dataset we used is Squad 2. It is comprised of a wide variety of topics, and each topic has a set of questions the model needs to understand and answer. So think of this as your standardized reading comprehension test, where you're provided a paragraph and a set of questions, and you need to find the answers to these questions in the paragraph. In our experiment, we want to distill BERT directly for question answering. We use distillation as our compression technique and run it multiple times with different student model architectures. Our teacher model is BERT pre-trained and fine-tuned for Squad 2, and we perform an architecture search during our optimization process to define the student model for each distillation cycle. We used multimetric Bayesian optimization to optimize the distillation process and perform our architecture search simultaneously. With this optimization technique, we're able to optimize for two competing metrics at the same time, and in this case, we tried to reduce the model size while increasing its accuracy. So at the end of the optimization process, we should see a populated Pareto frontier, where each point on the frontier is an optimal trade-off point where you cannot improve in one competing metric without sacrificing the other. So that's a very quick overview of the background of the project. And now we're going to talk about how throughout this whole process, experiment management was very critical for me. More specifically, it helped me with model development, understanding my problem space, and monitoring long runtimes. So let's look at how experiment management helped me with model development, and specifically with setting up a baseline and validating the feasibility of the experiment. So baselining is a very important process, an aspect of my model development process. Typically, I deal with models and data sets I've never used before and have no real intuition for. So after manually poking around the data set, I start to scope out an experiment design to achieve a high-performing model for my given data set. And to validate if this experiment is feasible and doable and worth the cost, I typically try out a variety of baselines to understand, one, what kind of model performance I can expect, and two, if the experimental procedure makes sense. So for baselining the BERT experiment, I wanted to understand, how should I modify the teacher model? What's a solid student model architecture? And how should I train the full distillation cycle? So the first baseline I tried included using BERT, fine-tuned on Squad 2 as the teacher model, using Distill BERT architecture as the student model architecture, and training the distillation process using the hyperparameters prescribed in the Distill BERT paper. Essentially, I wanted to see how much I can use out of the box without really varying anything. And to measure model performance, I decided to track accuracy for different properties of the data set, including answerable questions and unanswerable questions, as well as a composite metric that will be optimized to measure the total accuracy for the full data set. So let's take a look at what the trained model looked like. So this is a training run that I tracked through the SigOpt experiment management dashboard. So as we see here, the trained model has a 4% accuracy for this metric, which tracks how well it's performing for answerable questions. It does okay for unanswerable questions, but it clearly still doesn't converge. And we see the composite metric, which is this guy here, is actually degrades in performance over time and does not converge. So overall, this is very much not ideal, but by using this first baseline, I was able to actually conclude that using the teacher model as BERT pre-trained on squad 2 was in fact a good idea. So learned something from that. So next, I decided to try seeding the student model with pre-trained weights. This seemed like a good idea given the resources I had and how small the Squad 2 dataset is compared to the larger Toronto book corpus and the English Wikipedia corpus that BERT is typically trained on. The Squad 2 dataset is also similar enough to these larger corpuses that using transfer learning at this point for the student model training was a good idea. So I decided to keep the model and distillation hyperparameters the same from the previous baseline, as I expected the model initialization to really make up for this poor performance from baseline 1. So now the student model is the same architecture as DistilBERT, has pre-trained weights, and is trained on the same hyperparameters as baseline number 1 and the DistilBERT paper. So we're just going to take a quick look at what this baseline looks like. So here we actually see it performing pretty well for answerable questions. We see it performing pretty well for unanswerable questions and actually converging. And we see this composite metric that we are going to use to optimize for performance is actually also doing relatively well, and in fact does converge in a nice way. And this last curve is also something that we expect to see. So all in all, so this second baseline hit a 67% accuracy and has properties of a healthy training run. And this is a huge improvement. So the performance jump from baseline 1 to baseline 2 really validated my hypotheses on using these pre-trained weights. The higher model accuracy also lets me know that the experiment is feasible, but there's also room to grow, obviously, in terms of model performance. There are many ways to address poor model performance. I opted for leveraging pre-trained weights, given that it was a really easy resource to use, but you can approach this in many ways. So now I have a solid baseline model and understand that the experiment is feasible, but that's only a part of my larger model development process. And I now really want to understand what happens when I play around with the parameters for the distillation process, model training, and the model architecture itself. So this experiment clearly has a lot of moving parts, mostly which is I want to search for the student model architecture, tune the training parameters, and modify how the distillation process works all at the same time. And a quick way for me to understand how each of these parameters affects my model performance is to run a fast and dirty hyperparameter search. You can try this with random search, but I opted for a quick Bayesian optimization run. given the size and complexity of my search space. So this is the resulting Pareto frontier of the quick and dirty multimetric Bayesian optimization run for this experiment, with the 3 types of parameters that I wanted to search. So from this, 3 things pop out. We see that larger models don't actually perform as well, which is really interesting. There's this weird gap between 20 and 40%. And there's this interestingly small cluster that's kind of starting to form around the 50% exact. So we're just going to take a look to understand what we can learn about our parameter space given this quick and dirty Bayesian optimization run. Okay, so this is the graph that we saw already. Here we can play around with basically graphing what correlations each of the parameters has with the metrics and with each other. For atom epsilon, for example, we see that there might be this spot that actually prefers or leads to a higher accuracy, but it's clearly, there's really no correlation we can tell for our second metric, which is how big the model is. And an easy way to do this is to look at the parallel coordinates graph. So if we look at everything that performs at least a 40% accuracy across all sizes of the model, we see that there are these preferred areas and preferred areas of correlation between the parameters that actually lead to this higher model performance as well as lower model size. But if we look at what it looks like for models performing at 30% and less, there's really no correlation in terms of what parameters lead to such poor model performance. This is really interesting, but what it does tell us is these sweet spots are really what results in this jump from 20% model accuracy to the 40% jump that we see up here, which is kind of interesting. So by iterating over these parameters and looking for correlations, I was basically able to identify a handful of parameters that heavily influence the model's performance, which include the number of layers, the distillation loss, how much should soft versus hard target loss be weighted, all the dropouts of the network, and the distillation temperature. So as we saw before, the sweet spot ranges for these parameters leads to the drastic jump in model performance from 20 to 40%, which I was able to find by conducting this small Bayesian optimization cycle. Next, I really wanted to understand what's happening at this 50%, because we do see these configurations kind of merging together in this area, which we don't see as much in other aspects of the run. So we're just gonna explore a little bit. So we're gonna use, so this is our runs table from the experiment management platform. This is basically all of the runs for the project that I'm working under here. And what we want to do is we really want to understand what's happening at this very specific range of accuracy values. So I'm just going to filter them out. We're going to look at some graphs. So if let's just take a look at these two. So if we look at this, what we see happening is that these models in this cluster are unable to recognize unanswerable questions and are basically randomly guessing that every single question, they're unable to recognize answerable questions, and they're basically randomly guessing that all of the questions that it sees are in fact unanswerable. So we see this split where it has a 0% accuracy for this metric, but 100% on this metric, which is leading to an overall accuracy of 50% for the model, which really doesn't reflect what it's actually being trained to do. And we see this pattern across the training runs for each of the points in this cluster. So that's obviously extremely unideal, and we want to address that. And this really goes back to the properties of the data set. We see this model behavior because squad 2 is in fact split 50-50 into unanswerable and answerable questions, while answerable questions require the model to identify a specific span of the context as the answer. Unanswerable questions only need to be marked as unanswerable. So there's no span that needs to be found. And this makes it really hard for the model to perform well on answerable questions and easy for the model to randomly guess that everything is unanswerable and be right 50% of the time. So there are many ways to address this data property. You could create another composite metric to measure accuracy that takes into account the stratified nature of the data set. You could switch data sets or take this behavior into account downstream. But instead of having to do that or create another composite metric, I opted to include a metric threshold on our 50% accuracy. So now the optimizer essentially knows to focus on parameter suggestions that lead to a model performance greater than 50%, and will intelligently avoid configurations that we know will lead to the model randomly guessing and performing very poorly. So by using a small optimization cycle and analyzing its associated model training cycles, I'm able to better understand the parameter and problem space. And I'm also able to use that to inform my experiment design and iterate on that. The third thing experiment management helped me with is monitoring my full experiment real time. So after checkpointing, testing, and orchestrating my code, I was ready to run my full experiment that would run continuously for 4 days and would cost around $7 grand on AWS. And within 24 hours of launching the experiment, it was very clear to me that there was something wrong with the training cycles, as none of the model configurations passed this 50% threshold mark that I had set previously. So then I decided to look into the training curves themselves to really understand what it is that's going on. So I've just selected a random one from these points here, and they all reflect the patterns that we're going to see with this training run. So what we really see here is unexpected. We see that the model is doing really well for answering questions that have answers. But if we look at how it's doing for unanswerable questions, it's at 0%. So this really flipped what we saw before, and is overall unexpected because we were really concerned that it would randomly guess that everything is unanswerable. But what we see with this behavior is that it's unable to recognize any questions as unanswerable. So I went back to my logs, and as it turns out, I had not turned on a crucial flag, and the data set was being featurized incorrectly. Happens to all of us. So I fixed this flag and ran the full experiment, and this is the resulting Pareto frontier. So the yellow dots are the optimal points, and the pink dot is baseline number 2, the baseline that we talked about earlier. And by using this frontier, we're essentially able to understand the trade-offs between model performance and size during distillation. We're also able to identify architecture configurations for the student model that result in these trade-offs. So we're really able to answer the questions that we set out to answer. So how did experiment management really help me throughout this process? It helped with model development to design effective baselines and validate that the experiment was worth doing. It helped with understanding the problem space by helping me explore the parameter space and iterate on my experiment design. It helped with monitoring long cycles and tracking and debugging my runs real time. So why experiment management? At the end of the day, as modelers, we have to iterate and validate ideas very quickly and efficiently while getting an intuition for the problem we're solving. And many times that involves spinning up long processes with high compute costs and long training times. So even if we do our best to test all components, try baselines, and checkpoint everything, something could always go wrong. So having something like SigOpt's experiment management serves as a home base for me through all these moving parts and really just makes my modeling process more efficient and help me understand what decisions to make every step of the way. So thank you for tuning in. The full work is currently live on NVIDIA's dev blog and will be live on SigOpt's blog soon. We've had previous webinars more focused on the experiment itself. So please feel free to watch those. And we currently have a free beta open to try out SigOpt, including our experiment management solution. So if you'd like to join, please click the link below. Yeah, and now I'm going to open it up for any questions.
Cool, thank you so much, Meghna. That was a great presentation. We already have a couple questions added into the Zoom. The first one is, what areas do you see as suitable for future exploration in reducing the size or increasing the accuracy of your BERT model?
Yeah, well, I think there's probably a lot could be done. Off the top of my head, I would say it would be interesting to see how well this model performs across a set of other NLP tasks, because it was compressed specifically for question answering, but it would be interesting to see how this technique really works for other NLP areas, which is not really like a compression method, but more like generalizability. I know there's like a few other compression techniques out there. Distillation is just one of the easier ones to actually implement, but like quantization would be really interesting to try, and possibly DCCL. Yeah, so.
Cool. Speaking of which, can you use SigOpt to expand the training corpus to achieve higher accuracy or better abilities on domain-specific problems?
Yeah, so I would say in general, definitely. We have published work on how to use SigOpt and Bayesian optimization as a whole to actually augment your data sets. I would say for this work, I'd be more interested to, I think it would be interesting to see if we could increase the size of Squad 2. I think it would be maybe not as effective for this project, but I think other ones, yes, definitely.
Great. And how did you go about customizing the visualizations you used when you were tracking your runs?
Oh yeah, I think I understand this question correctly, but basically I knew I had to track a bunch of metrics. So while I was creating the code base, I actually had an idea of what I needed to track and what that would look like. So I used experiment management to basically do all the tracking for me. And it was nice because then I wouldn't have to switch back and forth between like TensorBoard or other tracking systems to see what was going on, because I was already using SigOpt for the hyperparameter optimization as well. So yeah.
Great. Well, thank you so much, Meghna. And to all of our attendees, we'll be sending out the slides and a video recording later today or early tomorrow. As Meghana mentioned, you can find the full blog series on NVIDIA's developer blog. And thank you so much for joining us today. We really appreciate it. And if you're interested, be sure to sign up for our experiment management beta. Thank you, everyone, and goodbye. Have a good day.